Okay, after a little bit understanding of this kind of process, okay, and some people actually currently we in most of the IC we use a CMOS process instead of only NMOS process. That's because for NMOS we can contribute more electrons on the source and the drain, right? But for PMOS, opposite, so you contribute more holes. They have different meaning because in the IC, if I'm using IC to drive some kind of current, you put up the current will be easier by using NMOS. You put down the voltage will be easier by using PMOS. So you want to have a speed for pull up and pull down at the same speed. So you need to put these two together, become complementary one. Okay? So NMOS has a one-side ability. PMOS have the other side ability. So if you combine these two together, either pull up or pull down, the voltage will be fast. Okay, so that's why people try to combine these two together, becoming we call the CMOS process. CMOS means a complementary. Complementary. So include the M and the P. So so they combine these two MOS's strengths together, so become a better performance of the circuit. Okay, that's the idea. So for NMOS process, the process need to start from the P substrate, right? But for CMOS process, we start the process on the N substrate. That means the silicon substrate is lightly doped with the N-type material, like phosphorus. And because we need to start the NMOS from the P substrate, so we need to locally generate the P area in N substrate. Okay, that's the first step. Then the rest step is very similar to the previous NMOS process one. So on the P well, we call the P select area, we can generate the NMOS. On the other side, N substrate, we can generate the PMOS. Okay, so we will dope in different type things. So here we dope the N plus, and here we dope the P plus. So here we dope the N plus on the P area. So this is a NMOS area, okay? So on the other side, you can see on the N substrate, we double the P plus here. So the other side, we become the P MOS area. So when we put them side by side, so the whole substrate become a CMOS substrate. So we can have both of the MOSFET on the same substrate, okay? Yeah, just for your information, okay? It's not very important to understand it in full right now. Okay, now I will go to the detail of each individual process, okay, to let you know how we make them. So all the IC fabrication process will go through we call the lithography process. Lithography means we need to transfer the structure from our design, from our mask, onto the material. For example, like silicon dioxide, aluminum, metal. We need to use in the process to transfer the image from the design, the mask, onto the structure. So this process we call the lithography process. And because of the lithography process, we are dealing with very small, tiny structure. So the cleanness of the environment is very important. Okay, so we need to operate the process inside the clean room. The clean room means that we don't have many particles inside the clean room. It's a clean environment. Okay, so we have a different class of a clean room, class from 1 to 10,000. That means, for example, if we have a class of 100 clean room, that means that we can find a particle the size more than 0.5 micrometer in a cubic foot, less than 100. So in the cubic foot area, you can find the less than 100 particles, fewer than 100 particles. So there's a level of cleanness. So if class 1, you can find only one particle. It's very, very clean. Okay. In a typical room, you have millions to 10 million particles in that kind of area, that kind of volume. So it's very dirty, like the case room here. Okay, it's not very clean. Okay, so you need to control the environment. Okay, because if you don't control the environment, the particle deposit on the surface will easy to cause the defects. Okay, for example, the wires were not connected correctly. It break. Okay, so they can defect if you have a 10% defect for each layer. Masking process, out you will yield like a 50% function failed device after 7 mask process, because you repeat the process, right, time by time. So the defects will be accumulated, become more and more defects. So even you have only 10% defects each layer, after 7 layers process, you got a 50% failed. So that's why clean environment is very important for this process. Okay, so let's come back to the lithography process. So, for example, you want to define, okay, the structure of silicon dioxide on the surface. Remember, after every time you grow the silicon dioxide or you deposit silicon dioxide onto the surface, the material will become a film to cover the whole surface. Okay, so this is our work. If you want to define the structure, we need to use in a spatial way. We call lithography. So lithography is by first we spin coating on a positive photoresist or negative photoresist. We call this very spatial material. It's organic material. It's very sensitive to the light exposure. So it's called a photoresist. Okay, so we spin coating, so it becomes a thin film. Like your mask, you put your mask on your face, right? So it becomes a thin film on the surface. Okay, and after that, we bring our mask. The mask is, we have some kind of a opaque area and the transparent area. So for the opaque area, when you shine the light through the mask, the opaque area will prevent the light directly exposed onto the photoresist. But for the transparent area, the light will go through and expose onto the photoresist. Remember, the photoresist is sensitive to the light exposure or special light exposure. So for positive photoresist, when the light is exposed onto this area, the chemical structure will change from hydrophobic in become hydrophilic. So later on in the developer, so the exposed part will be developed away, dissolved away. Okay, so there will be no photoresist here, but only the center part without the illumination of the UV light, because UV light has been protected, has been shadowed by the masking area, the opaque area. So this part is not exposed to the UV light. So this part will remain on the surface as a protection layer. Okay, so now we protect only the center part, but the border part has been exposed to outside. Then we can put these things into, like, for example, like wet chemical etching. So for silicon dioxide, it can be easily etched by using hydrofluoric acid. So we expose the window part, the whole, actually immerse the whole wafer into the hydrofluoric acid. So the opening part can be etched away, can be dissolved away. Okay. So end out, only the protected area will remain. So that forms the structure. Okay. So at the end of the process, you remove the photoresist. This is only the temporary material you put on the surface. So after finish the process, you take the material out, and then you get the structure. Very tedious, right? So you may think, wow, so tedious. It takes more than 10 steps to finish the process. So is it worthy to use this kind of tedious process to do the fabrication? Maybe you have this kind of question. Actually, the good thing is that actually the process is tedious. I agree. But the question is, you want to fabricate thousands of this kind of sense structure together. You want to do it by use a hand, do it one by one. It costs a lot of time. So the powerful things for the lithography is we can do this kind of fabrication at once for thousands, even 10,000s of pieces of the device together onto the same substrate. So even though the whole process is very tedious, however, you can fabricate thousands or even 10,000 of this kind of device together, so still save a lot of time. Okay, so this is called batch fabrication, mass production in the IC industry. The process is very tedious, but we fabricate the thousands, 10,000 at once. Okay, so that's why we used to cost down. Okay. Okay, so all the structural definition need to go through the lithography process, and each lithography process will take one mask because you want to define, okay, the structure. So you need to use the mask to define the area of the structure you want to retain on the surface. Okay. So usually we use the number of masks to judge the complexity of the IC process. If you use more masks, that means that the IC process is more complex. So typical IC process would easily take 5 to 10 masks, depends on the layer of the metal on the top. Okay, okay. And I can remember my PhD work on the inkjet print head. I used 13 masks. 13 masks. So imagine how difficult it is. So if you have only 10%, 90% yield, after 13 mask process, you can tell only like 10% will become the final, unfailed device. So not very easy. Not very easy. Yeah. So in your process, I encourage you don't use too many masks. Okay. Try to reduce the number of masks. They can increase the yield of your fabrication process. Okay. That's a lithography. That's an important step. So for the lithography process, the detailed things, we first need to go through the wafer cleaning because we want to remove the particles. I will not go to the detail. You can look into the detail later. And also, by remove the surface particulates, we need to use like a very clean water. We call it DI water, deionized water. Deionized water means we take out the ions from the water, so the conductivity becomes very, very low. Okay, so when you measure the conductivity, it's like 80 mega ohm DEC. So it's pretty low. It's highly non-conductive water, high purity water, and also with not many particles inside, and also the bacterial inside. Bacteria is also sometimes contaminants. And the second wafer cleaning process, actually we go through several steps to remove several things, including the organic things, to remove the light metals and also heavy metals. So for organic things, we need to use different solvents. For the heavy metal, we're using like the ammonium. It's called RCA1. And for light metal contaminant removal, we usually using like a piranha, like using hydrofluoric acid and hydrogen peroxide, the mixture. And after this process, actually the surface of silicon easy to form a very thin layer of silicon dioxide. We call it native oxide. The thickness is around like 5 nanometer, typically, okay, within like 1 hour. Yeah, tens of minutes to 1 hour, you form native oxide easily. So we also need to remove the native oxide as well, okay, to make a good connection from your metal to the silicon structure. Okay, so these steps are used to do very clean, very good cleaning on the silicon surface. If you don't want, if your process does not have those kind of combination, maybe you can use a partial of them, not all of them. For example, you don't have a metal combination, you don't have a heavy metal, light metal. You can use only the first one, organic removal process. Okay? And also some oxide removal process, on these two processes may be necessary. Maybe it's okay. Sometimes if you don't care about the oxide on the surface, you already have oxide on the surface, so you can use only the A part to do the cleaning. Okay. 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 So so this is the first process on your silicon substrate for lithography. You need to clean the surface without any particles and also contaminants. The second one, you apply photoresist. So the application of photoresist, you can use the spin coating process. Okay. We need to deposit photoresist onto the clean and dry wafer surface. Okay, and sometimes we're using adhesion promoter to promote the adhesion of a photoresist onto the surface, usually using spin coating process. Okay. After that, we need to do soft bake. Soft bake means we need to remove some of the solvent from the photoresist and to improve the adhesion and onto the surface, using it at a lower temperature. Okay, for a very short time. Okay. Then we will do the alignment. Maximum alignment means because we use several different masks. So every time using the mask number more than 2, you need to align onto the previous mask or previous structure. So we need to have some alignment mark. Okay. So for alignment mark, we have 2 different kinds of mask. We call light field mask or dark field mask. For light field mask, that means on the mask you can see the structure like islands, opaque structure like islands on the surface. Most areas are transparent. Okay. So in this case, the alignment mark will be either like the box or like a cross. Okay. So your second, when you put your second layer of your mask onto your first layer of your alignment mark, the end will look like this, the bottom one. So if you design the first one as a box, the second one as a cross in a light field mask, so when they stack together, you can see the bottom one. So it's good to have this kind of relationship, so you can do alignment easily. You can see both of the alignment mark showing on the same window. Okay. However, if you do it wrong, okay, the second row is a wrong design. The first one is a smaller pattern. The second one is a larger pattern, opaque pattern. So when you stick the second one onto the first one, you won't see the first pattern. If you won't see the first pattern, you cannot see the relationship between these 2 patterns. You cannot do alignment. So this design is wrong. Okay. So maybe put a cross here to remind you this process is wrong. The first row, the first column is correct process, correct design. So this is for light field mask. But for dark field mask, it's an upside. Okay. So you need to design the first one smaller. Okay. The second one larger. Because for dark field mask, that means most of the area are dark. Only the marked area has opening. Okay. Clear view. So if you design this one, the second one larger than the first one, you can end up with both of the mark showing on your view on the vision. But if you design it opposite, so you won't see the first pattern. So it's not correct. So you can remember this column is wrong. The second one is correct. Okay, the design for alignment. So after alignment, you need to do the photoresist exposure. Usually, the photoresist has been designed to be sensitive to different kind of UV light. Okay, so typically the wavelength is around like 350 to 450 nanometer. Okay, depends on the vendors. Depends different companies. Like offer different kinds of photoresist. So photoresist, there are basically 2 kinds of photoresist. Okay, so when you have the mask, the opaque area is in the center here. Okay, so if you on the substrate, we already spin coating on the photoresist. So when you shine the UV light onto the region, so light can penetrate through the transparent area, the area here. Okay, so you have a positive photoresist. The exposed area will be dissolved away later on. So you remain the structure exactly the same as you've seen on the mask. Okay, so in this case we call the photoresist as a positive photoresist. So remember, the positive photoresist will give you the structure exactly the same as you've seen on the mask. But for the negative photoresist, it's opposite. So those exposed area will be closely linked and remain on the surface. The unexposed area will be dissolved away by the solvent. So the structure formed will be opposite to your mask structure. So this resist we call the negative photoresist. Okay, so the structure is negative. to your original structure. Okay, it's easy to understand. Yeah. So sometimes it's also interesting. We can using this kind of technique by using the same mask, but we can generate two different kind of pattern. Sometimes it's important because sometimes your professor want you to fabricate like a column arrays. So you can use positive photoresist to generate column arrays, right? But after a while, after testing, the column is not a good structure. Your professor want you to make a whole structure. So you can use exactly the same mask because the mask fabrication is very expensive. Each mask will cost you $1,000 to fabricate. So you don't want to do it again. So you can use negative photoresist to reverse the image. So the image will change from the rods into holes. Okay, become opposite image by using the photoresist lithography process. Okay, there's some technique you can apply in your real life. Okay, so after the exposure and also developing, you got the structure you want. So the area you have the photoresist. That means this area, the material underneath will be protected by the photoresist. So after the etching process, the rest of the material will be taken out to remain only the structures which has been already protected. Okay, and so after exposure, and also before you want to do the etching process, sometimes we need to do the hard baking. The hard baking means we need to harden photoresist to further improve the adhesion between the resist to the substrate. To prevent the wet etching, the chemical will penetrate through between the photoresist and the bottom material. In that case, the material will be etching underneath the photoresist. It's not good. So we need to have a good adhesion between photoresist to the material to have a good protection. So in that case, we need to have a hard baking process in a higher temperature. Okay, so purpose is different from the soft baking. Soft baking is only for remove the solvent, but for this one, we need to remove the rest of the solvent to harden the photoresist to have a good adhesion protection. Okay, so after the hard baking, we need to go through the etching technique. Now, typically, we have two different kind of etching. We call the wet chemical etching and also dry etching. I will not go to the detail because those things will be covered in whole in the level fabrication process. I just give you a rough idea. For wet chemical etching, for example, we will bring the material to contact with some kind of acid or basic for etching. For example, like silicon dioxide. Silicon dioxide is easy to be etched by using hydrofluoric acid, HF. Okay, so you bring the silicon dioxide open window directly contact with the HF, like BOE or BHF, which contains the ingredients of HF. Okay, so can be etched. For silicon nitride, like a phosphoric acid, okay, it's etching. And aluminum, it's like phosphoric acid and other some kind of different acid together. Okay, so wet chemical etching, that means using wet chemical to do the etching process. So in this case, the photoresist adhesion is very important. Okay, because when you leave the material inside the wet chemical process, if the adhesion is not good, the chemical can go between the photoresist and the material and do the etching underneath. Okay, this is the first part. Okay, wet chemical etching. You can also consider using dry etching. The dry etching process does not use any wet chemical. Okay, so it's formed inside the plasma chamber. Okay, it consists three different kind of method. First one is called plasma etching. The second one is called sputtering etching. The third one is called reactive ion etching. The differences are the plasma etching is pure chemical etching. Okay, in the wet chemical etching is a chemical etching based in the aqueous environment, in the wet environment. But in the plasma etching is in the gaseous environment. Okay, so those are gas types etching. They can do chemical reaction on the surface to remove the structure. It's called plasma etching. So this the etching is performed by chemical way. Okay. So in opposite, sputtering etching is not using chemical way; it's a physical way. Okay, using special ions to knock out the material you don't want. So it's a physical way. So reactive ion etching is a combination of the plasma etching and the sputtering etching together. Okay, so it consists of the chemical way and the physical way together. So for dry etching, the difference between dry etching and the wet etching process after the etching, you can see the profile. For the wet etching, because it's isentropic, that means no direction preference. So when you do the etching, we'll start from this position to the inner part and to the downward part and to the inner part as well. So the profile will become a little bit slope. Okay, it's not a very steep. Okay. It's like a very not a very steep, but for dry etching you can get a much steeper, okay, much straight, sidewall, okay, from a chemical, gas type chemical etching process. Okay, maybe we can stop here and take a rest. Okay, and we'll come back 10 minutes later. Thank you.